Are you recording? Testing. Yeah. Is the volume okay or is it too loud, right? Yeah. How about this? We better? Yeah, okay. Yeah. Sorry for being a little bit of late, but let's start. Today we will learn about the system calls and then page fault as the next step for the after learning about the interrupt handling. We've learned that the system call is also using the interrupt handling mechanism for mediating some of the computations between the ring 0 and ring 3. And then we will learn a little bit more details about those system calls. And then we will move forward about like how such interrupt handling can be used for the doing some real useful things. So the one of the things that I feel is like you guys could also feel that in this class, you are learning something, getting down to the very low level and then moving little up. So there are many of students feeling that like that while you are implementing virtual memory, then like right now, you don't know how it will be actually being used, but you know that it is like a virtual and physical address, and then it's tightly mapped and then working with the page table, those kind of thing. But as the lecture goes by, what you will see is like we are actually diving into the deep down here and then going up and up and up again. Yeah, and then when you finish like the next month or something, then you will see that what we are learning at the bottom level will be connected somewhere at some of the high level ideas. Then like at the end of the term, you can think it as like those kind of the low level ideas are linked with the high level ideas, and then you will be clear about how the internals are working. And the reason why I'm telling like this kind of thing at this time is like once you see that how the page fault handler could be used in the reality, then like you will feel that you guys are studying the important concepts of the operating systems. And then hope you guys feel that like at the end of this lecture, you guys feel also about like how I just mentioned. Yeah. So let's do a little bit of recap about like how the user kernel execution switch happens in the operating system. So although we separate the ring 0 and ring 3 with the memory privilege, so the only thing that separates the privilege is written in the page table. So PTU, the presence of that bit, yeah, we determine it is a ring 0 or ring 3. Yeah, that's it. And then we enforce that by jailing. So like jailing the entire execution of the user level within ring 3. So whatever the program runs in this kind of the user level application. So in the ring 3 virtual memory space, yeah. We do not assume that like these programs are benign. We do assume they could do malicious steps such as like the while one or like the keep invoking fork system call to like drain the entire system resource. But even we assume that at the operating system level, because we have the higher privilege than the user program, we can mediate such request and also kill the program if required. So we can do so. And the reason why we can do that is like we do not give the privilege that the applications directly talk to the hardware devices. And for doing that, we just let only the operating system can talk to the hardware, and then ask user applications must request the operating system for doing something. Then one interesting thing is that like when this kind of the user kernel switch happens, then we might apply some of the security checks if this application is doing correctly, and also if this kind of the console request is legitimate to the application. So that is the thing that we will learn about the system call today. And then to do just the recap, and then after the operating system handle these kind of requests, because the only way we learned about the transitioning from the ring 3 to ring 0 is via having an interrupt. So to return from the ring 0 to ring 3, we use interrupt return. And then the reason why I have like these kind of the two hops, so one library call and one system call, and then irit and return is that to distinguish system calls from the library call. So for today, we will learn a little more about the system call and then how we can use the system call as some of the security mechanism for protecting the operating system while letting the other application use the functionality of the operating system. And the other thing we will learn is like about the page fault handler. So I told you that there's a exception and faults, and then exceptions are the things that we cannot recover. And then you guys might be curious about like what kind of faults are recoverable, and then what will be the useful case of that. And for that kind of things, I will give an example of like how we can implement automatically growing stack and also the copy on write and real virtual memory using the disk space as also like virtually the RAM kind of thing as with the mechanism called the swap. Yeah, and then we will learn about like how these things can be implemented with the use of the page fault handler. So let's start with some of the conceptual thing about like the ring 0 and ring 3. And the reason why we have a separation between ring 0 and ring 3 is that because we don't have trust in these kind of applications. So you guys had heard about the ransomware, something like downloaded from the internet and then execute it. It tries to read all your file and then encrypt it, ask for your Bitcoin or something like that. And the reason why that kind of thing happens is that except for the ring 0 and ring 3 privilege separation, in the most of your desktop, you use like, applications with your account name. And that means if you run any kind of application, then that application can work as on behalf of you. So do whatever you can do. So that's why they can read about your memorable photos and then encrypt it and then store that into somewhere weird location and then ask for the Bitcoin. So to prevent that kind of attacks, so I think that preventing the ransomware could be a little bit difficult, but one of the ways like if we create all the cryptographic functionality as like a system calls, and then like if they have to call a system call to do that kind of functionality, or then like we can catch it. So like some people like make an assumption that if the ransomware calls lots of cryptographic library call or something, then it could be suspicious. But I don't like that kind of assumption because we can write our own logic for encryption, then that assumption will never work. But the one thing that ransomware cannot avoid is to read and encrypt and store back the data. They should use file-related system calls to work with the disk, because operating system nowadays, they do not let applications directly work with the disk. They must call open, read, write, those kind of system calls. Then if we monitor those kind of system calls at the operating system level, and then if one of the applications invokes too many system calls or file opening, closing, those kind of things, then we might detect that as some of the anomaly for the ransomware and then kill that. Now, I know that like it cannot prevent like a ransomware attack 100% clearly, but you can get the idea of like how the operating system may work for like after detecting the reading and writing of the file system calls for 1,000 times in a second or something. Then it could be a little bit weird for the regular desktop application, so that kind of decision could be made. So because we have this kind of the ring 0 and ring 3 separation, the advantage that we can gain is like we do not have to assume that the programs are benign. So we just let the programs could be completely go wild, but at least we can have something protected in our system and use that to protect use that to prevent like some dangerous operations to the entire system. So by just having the ring 0, what we can kill is like we do not let these applications directly talk to the hardware. So if they try to flash our BIOS or change the boot order, for that kind of things, user level applications cannot do that. Yeah. So that is the one concept. So the most importantly, operating system tries to block this kind of thing, yeah, because we don't trust these kind of applications. Right? And then one of the important ideas is that because we do not let the direct hardware access to the Ring 3 application, they must go through the operating system, and that's the rule in our world. And because we have that kind of hook, so every time the application need to do something with the hardware, they should come to the operating system. So there's a one gate that we can check everything. So you can think it as like this is a TSA gate at the airport. So whenever you want to get into the US, you need to get through that kind of the check, security check, right? And then operating systems can use this kind of a system called gate as a checking gate of the every applications. And before getting into more detail about like this system called gate, let's making the things clear about the distinction between the library calls and system calls. So most of the APIs that you guys are using are library calls. So when you're writing the Ring 3 applications, so just in general programming, there's no reason that you guys need to directly talk to the system call. And then because the system calls are specific to the operating systems, so many of you just learned about like some of the standard in Python and C, C++. These are standard in language. And then C programs runs on Windows, it runs on Linux, and runs on the Mac OS. And the reason why it runs on any kind of operating system is like it has a compatibility of a layer that is so-called the standard C library. So that whenever you try to open a file, maybe you will use the standard C library, such as fopen kind of the API, or you can use like a direct API, such as open read write. But those kind of the APIs are already implemented in the C library of the Windows, and then that C library automatically translates your use of the functions into the operating system's use. So what that means is that, so for example, you could have these kind of the read function in C code or something, but in Linux, it will directly invoke the system called sysread, but in Windows, it will invoke some other system call for Windows for like a file opening. Yeah. So the important thing here is that you can regard most of functions you are calling in the Ring 3 application. These are all library calls. But internally, if they really need to interact with the hardware, they will call the corresponding system calls. Yeah. So the important thing is like where the code is executing. So you can regard the system calls as the real request that the application indeed requires some of the access of the hardware and so on. So basically, your applications will make a function call to the library call. And then in the most of cases, this library call will make a system call for you. Yeah. So most of the system calls would be hidden from your side. So that's why you have not seen these kind of the details a lot. But when it's right now, you guys are implementing about the system call. So that's why you need to understand these kind of details. And then, so to get into one step further, so what that means is that whenever there's an application API that uses some of the library call, for example, printf, scanf, send, for these kind of things, we know that these functionalities will interact with the operating system, interact with the hardware. And then they internally calls these kind of the system call, the counterparts that the operating system handles for these kind of APIs. Yeah. And then important thing is like these APIs are in the unprivileged area, and then these APIs are available in the privileged area. Yeah. And then the reason why we have these kind of the layer is that our application do not have the privilege to interact with the hardware, but the operating system has. So the main reason is like we are actually requesting something to the operating system and then get the result, and then everybody will happy. But think about some of the problem. So suppose this application uses these three functionalities. Then for the operating system's point of view, it's okay to allow them to access the write, read, send function whenever they requested these things. But suppose the operating system has some other functionality. Then if the application creates some of the bad function, and if that directly calls to some of the function that is not available in the system call, then that should be prohibited, because so it's something like someone is there, the operating system, someone is there and it's privileged and then can do everything. And then we as an application, we are asking operating system to do something. Then one of the things that we can go wild and bad is like that if we fool the operating system and ask something else than I should have do, yeah. So it's like killing the machine or format the disk or something like that, then it should not happen in the system if the system to work it correctly, right? So to protect the operating system from like the applications request, the random request, and then accept that. So system call is not designed like allowing any kind of access to the operating system. Yeah. So if we just open all the function addresses and the let application call the function, then something bad could happen. So the important thing is like what we need to do is we only need to let the application calls only for the allowed functions, not the random arbitrary functions like this. So we need to do something like this, block everything else, then just open the gate for the allowed system call, then it will be okay. Otherwise, applications can invoke a format or some other functionality, then it could go wild. So we need to protect this kind of request. We need to prevent that. Yeah. So we designed the system call with the concept called as a call gate. And then what the call gate is doing is like very simple. So that it sits between, so it's just a conceptual thing, so that you guys actually see the implementation of this thing. So the implementation is via the interrupt, and then at the thread handler with the switch case, we check the system call number and then only invoke those functions. That's how we implement this kind of call gate. But conceptually, we can place some of the TSA gate-like thing in between the app and the operating system. And then whenever some request comes from the unprivileged ring 3 to the ring 0, then it will goes to the thread handler, because we will use interrupt to handle system call. And then whenever we have an interrupt, it will call the function at the IDT, and then we set that as a thread handler in JAWS. So whatever request comes from the application will arrive at this thread handler. And then if we write the code to just invoke these system calls, and then do not write the code for like doing anything else, then we can protect that. So we can theoretically kill there would be no way that the application can invoke this function by having this kind of gate. And also we can do a lot more security checks at there. Yeah. So that's the conceptual stuff that how we design the system call, and then allowing that only the benign functionalities to the application, and then disallowing any kind of the arbitrary execution on the operating system side. And we implement this call gate via interrupt handling. And in JAWS, we use interrupt 0x30, so 48, remember that one. And then in Linux, it could be 0x80. In Windows, it could be 0x2e. But because this kind of the interrupt and then interrupt handling and interrupt return. So it takes a little longer than the switch of the ring. But so before 1998, I believe that's the year that when the Pentium 2 was born. So before the year of the 1998, there was only one mechanism that we can invoke system call, that was via interrupt. But interrupt is a general mechanism. So general mechanism for handling exception, fault, interrupt, real hardware interrupt, and also can handle system call. But the only requirement that we need for the system call is that whenever user space request, we should have like some way to raise the privilege and then execute something from 3 to 0. And then we need to catch that in one single handler. So that's the requirement for the system call handling. And what that means is like we don't actually need the entire routine for the interrupt handler or something. So because interrupt handling, I'm not sure for right now, but it usually takes around like the 10,000 cycles because like it need to stop all the CPU and then get into some of the certain state to handle some of the interrupt or something like that. And because interrupt handling has like a much more functionality than it is required for handling the system call, CPU designers have added new instructions called the sysenter, sysexit. So from the name, you can see that it's for system call. So the sysenter means that it will be calling a system call from the user level to the operating system. And then sysexit is like the opposite of that. So you can think it as like the interrupt irate, sysenter, sysexit. And then after having these kind of instructions in the 32-bit, when the AMD designs a 64-bit x86 processor, they knew that there's a requirement for the syscall, syscall, and then they created new instructions called the syscall and syswrit. So that nowadays we use syscall and syswrit for the system call. And then I'm not sure it's not that accurate, but sysenter, syswrit, syscall, syswrit is more than 10 times faster than like an interrupt-based switching. But this is somewhat historical thing. So fundamentally, what we need is like some of the mechanism that we can jump up the privilege securely. So in JAWS, we learn it as a traditional mechanism as an interrupt handling. But please note that there are some other ways to like switch the ring from the ring 3 to ring 0 to ring 3 to ring 0. Yeah. And then we may use like these two other instructions, but conceptually it's the same. These instructions are a little bit faster. Yeah. And then because we restricted the way that the application requests operating system for some functionality only with this mechanism, then at the system call handler, we can catch any kind of the request. And that means whenever application makes a system call, it could be via interrupt or sysenter, syscall, anything, then at the system call handler, something like this, call gate, yeah, we can perform some of the checks if the application is allowed to invoke this system call or how many of this system call has been executed. For example, of like a detection of the ransomware kind of thing, so that we can perform that kind of thing. Yeah. So let's take an example about like how an operating system applies some sort of the security checks for some of the system call. So suppose you have a read system call. What read system call does is like
what time are you meeting,
some of the data. Wait a second, I need to mute all the students in the Zoom. Yeah, okay. So what read system call does is like at the system's point of view, it accepts some data from the hardware or somewhere, and then put on some of the system's memory. So although it's a read operation to us, so we are actually apply some of the write operation on the memory. because if the system read the data, then it's actually writing some of the data into some of the memory location. So for example, if we invoke file descriptor, buffer count, and this kind of thing, then it will accept this file up to 512 characters from the console and then put the data in this buffer address. So in this case, there's no problem because like the user space data, and it will accept some of the data into the user space data. So that's all okay. But think about that. So if you take a look at the JOS memory layout, so you guys know that the ELF handler of the JOS kernel will ask us to put the JOS kernel in the physical memory 1 megabyte region. Yeah. But although we do not have access to the physical memory, we have a direct map area at the top of the 4 gigabyte virtual memory space. So current base plus 1 megabyte. That's the address of the virtual address of the physical address that stores the kernel. And then right now the code is a little wrong, but think about, I put this address as the buffer address. Then it's something like, please read from the console, but could you put the console data into the kernel code area? Then if I type something, then we can directly modify the kernel code. And then that should never happen, right? Yeah. So how this call gate prevents this kind of attack is that, so whenever there's a read system call comes in from the user space, what this call gate need to do is it needs to check the arguments and then check if this address is a user address or a kernel address. So if it is a user address, just pass it and then apply sysread, and then everybody will be happy. But suppose I supply the kernel address here, then operating system need to check it, check the argument. Oh, this is a kernel address that you do not have the permission. Then we need to send the error message to the user. That's how we can use call gate to prevent some of the malicious use of the operating system functionality. So I wrote the one simple example so that to give an idea that this is the real thing. So that I implemented this application. What it does is like for the first time, I just put the buffer address in the user space and then see the return value of the system call. And then next time, so this address is the kernel address for the Linux definitely. And then this is where my Linux kernel is located in the 64-bit machine. And then I just tried this address to make an attempt that from the console, I tried to like fool the operating system for letting me editing the kernel code directly. Yeah. And then these are the return value. When I type like 8 characters and I enter for this one, because this system call has no problem. The addresses are all user space, and then it's allowable. So the operating system allows that. I typed an 8 character and then enter key, so that it just returned 9 characters, 9, because it accepted 9 characters from the console. But for the second system call, it just gave -1, and then the key error will print out the error, and then it says bad address. Because operating system has checked that and then returned the corresponding return value for the bad address. And to show you it more detail, so let me tell you about the one tool called the strace. So the strace in Linux is a shortened form of the system call trace. For example, if you run any kind of program, for example, bin ls, those kind of program attached with the strace, then it will show what kind of system calls the program invokes. And then this can also work because we have a system call gate. And then every time the application calls the system call at the hook, we can print out this kind of message. Yeah. And then I ran the same program, and for the first read, it worked well, returned a 9. But for the second read, I supplied the kernel address, and then it returns -1, bad address. Yeah. That's how it works. And then another tool is like you can also monitor library addresses. And then there is a tool called the ltrace. then you can see that what kind of library calls are there. And there you can also see the thing. But at this time, our focus is more on the system call side, because we are focusing on like how the operating system interacts with the user level application. So in summary, so system calls are something like the operating system has some of the privileged service, and then they are opening APIs to the application. But if we just open the entire API of the operating system, then any kind of the user level application we don't trust, they can directly call weird functionality such as format. Yeah, we don't want that. And to prevent that, we create a call gate. And then at the call gate, what call gate means that all the system calls need to come to here first. Then we can check whether they are intact or not. And then we can kill or reject any kind of the bad system calls. And the way of implementing call gate is like we will creating only one way to get into the system call. And then right now we are doing that with the interrupt handling. Yeah, but it could be a little bit getting faster by inserting new instructions such as a syscall, sysread, or sysenter, sysexit. But the same thing is that the important concept is that we are letting the user space having only one way to invoke the system call. And then that's the call gate. And then at the call gate, we can examine the arguments, and we can check that to prevent some of the bad thing happens in the operating system. And then this is directly related to the last part of your lab 3 assignment, because at the end of the lab 3, it requires, after implementing all the system call handler, it requires you to write a function called the user mem check and user mem assert. And what that function does is at the system call gate, or like at the start of the system call, you need to do require the security check to prevent some of the bad things happening from the operating system. Any questions up to this point? So if you understand that this is actually similar to some of the border control, yeah, we have only one way to get entered to the US, and then to enter to the US, you need to get past to the customs and the border protection, something like that. And then we are doing the same thing at the operating system. And then next is about handling fault. Yeah. And then there are many faults, but the reason why I like to just show that the example of the handling of the page fault is like this is the most popular one. And then like I believe that there's indeed not that much examples that we could utilize like by handling the fault, but handling page fault can support like lots of the general functionalities. So that's why I like just giving an example of this one. Yeah. And then the difference between the fault and exceptions are like the exceptions are something that we should stop. We cannot recover, but the faults are something that we can recover. And then maybe you guys still think like if there is a page fault, something wrong happens in the page table and page directory, those kind of thing. And then if there's any kind of error in lab 2, it stops at assertion. But you guys might think that what I'm talking is somewhat insane, because like if we did a mistake on the fault paging, then it should stop. But what kind of the things that we can recover? So it's not about like we have a mistake in the assigning the virtual to physical address. It's more likely we are intentionally inject some of the page fault. And then whenever that happens, we will handle that to do something more. Yeah. So the important thing about the fault is that we can resume after handling the fault. Yeah. And then the case of the page, the exact condition that the page fault happens is that when we stop at any kind of the virtual to physical address translation. So it could be fault by invalid translation. For example, if the PTP is missing, if that value is 0, then the address is invalid. Then it could generate the page fault. Or if the CPU attempts to write on the read-only memory, then it will generate the page fault. Also, if the application tried to access ring 3 application attempts to access ring 0 address, then it will also generate the page fault. But still, you guys might think that like these are all the violations. Then how can we recover? Yeah. But before getting into there, let's take a look at a little more detail about the page fault. And this is the code snippet that I wrote. And you can regard that this is a user level application of JOS. And then inside of there, because I know that kernel base plus 1 megabyte is where the kernel is stored as a kernel virtual address. And then in the user space, what I did is like I attempted to access that memory and then try to write the exclamation mark in that memory. So that instruction is just like storing this value into this address. And if you try to run this, it will generate this kind of default at the trap handler. So because right now you don't handle the page fault so what that means is like whenever a page fault happens, like it just print out like what's happening. And then the important thing here is that if the page fault happens, then we can get several information from these kind of the trap handler. So the first thing we can get is that when the page fault happens, CPU automatically stores the the address that generates a fault into the CR2 register. So take a look at the CR2 register here. Then you can see that the F010064, and then that was the address that this application actually accessed. So the one thing is that we can get the idea of like which address generated the fault. And then another thing we can get is that it has the error code. Then error code stores the reason for the why we have fault. And then you can take a look at some of the details of like the Intel document about these kind of thing. But in JOS, it kindly described that what these error code means. So the fault was, it was a write accession, write access, and then it was a user mode access. So like the user mode tried to attempt to access the kernel. That's why it fault. And then it does not have a writable access, but it tried to attempt the write access. That's why it has a fault. And then the protection fault means that the fault was generated because like it does not have like the kernel privilege at all. So that we can get some of the reason about the fault here. So basically the page fault handler. So at the page fault handler, whenever fault happens, we can get the idea of like why this fault happened, which is the problematic and the address, those kind of things. Yeah. So in this example, we supplied this kind of address, and then 7 means like all 3 bits are 1, so that you can interpret about like that kind of the error messages here. And up to this point, you guys don't know about like how we can utilize this. But let me give an example of like how we can utilize this kind of the page fault and then do something more. Yeah. So, and then before that, let's take a look at how the operating system may handle this kind of fault. So the example that I just showed you is like in the user space program, I just attempted access to any kind of kernel address. And then CPU will generate the page fault because it does not allow for the user level access. Yeah. And then it will put the faulting address to the CR2 and then put the error code. And then in the IDT, CPU knows that it must call the page fault handler. So which you defined as a TPGFLT, those kind of thing in JOS Web 3. Yeah. Then the operating system will go through trap handler EC because it has an error code, all traps, trap dispatch, and then page fault handler. Yeah. And then at the page fault handler, if you take a look at some of the snippets in there, then like it already has like some of the snippets of like the reading CR2 or those kind of thing. And because like we can get the idea of like the reason of the fault and then which address was generating the fault, those kind of information from these kind of the thing. But thankfully, because just stores every register values in the trap frame, and we can get all these kind of information. And what page fault handler need to do is like after getting these kind of information, we could just fault if it cannot be recoverable. But if it is recoverable, what we can do is we can resolve the error and then continue the execution. Then what it will do is it will go back to the problematic execution instruction again, and then run that instruction again. And then what that means is that previously it was page fault, but at the page fault, if we map that address as something else, and then making as accessible, and then get back to the user space, then user space can try to execute that instruction again. And if there's no problem, then they can move forward. Yeah. So handling the fault is something like that kind of mechanism. So at one time, it could generate the fault. But at the second time, if the operating system resolved the fault, then user space can move forward. And now let me give an example of like how you guys can utilize this to do something else. So the first example is about like the automatically growing the stack. So if you take a look at the memlayout.h of the JAWS, you will see that for the user level stack, we just mapped to just one page for the user level stack. But that means is that we only map the one page for the user level stack and the next page is not mapped. Then suppose you are using the large local variable bigger than 4 kilobyte. Then there's no stack space because your stack space is just a 4 kilobyte, one page. Then the program will fault. And another thing is like, suppose you are writing some of the recursive function. And then if your stack frame hits the 4 kilobyte limit, then it will also crash because there's no mapped memory at all. Yeah. So it's something like this. If you create like the 8 kilobyte buffer in the stack and then try to access that, then it could generate the error because it's not mapped. Yeah. Then my question is that, then can we design the operating system whenever there's a page fault happening by the not having the enough stack space, then at the operating system, can you catch that and then map the memory and then continue the execution? So we can actually do that. So we can implement some of the on-demand stack growing. Whenever program requires it, then we can supply that. Yeah. So that we can detect this kind of a fault whenever the program accesses out of the bound or something. And then we can utilize the page fault because, so in this case, so when this function defines this variable, we did not use that at all. Yeah. But at the time of the accessing buffer 0, it will access somewhere down there. Then, because this area is not mapped at all, it will generate the page fault. But at the operating system, what we can do is check the CR2 register. If the CR2 register points to we know that how much of the current stack is mapped for the user application. And then if that is just below, one page below the current mapped stack or something, then we can presume that that's overflow on the stack. Then what we can do is just map the page and then continue. Then at the first trial, it was page fault because there's no backing physical memory. But at the page fault handler, we can add the physical page. Then at the second time, we run this one. then it will store the value into the valid memory. That's how we can utilize the page fault handler to back some of the requested memory, and then continue the execution at the user side to make it as if operating system can catch and handle on-demand stack allocation. So to get it with the more detailed example, suppose we have a function like this. The reason why I have a buffer with the size 32 is like I would like to demonstrate how it works is like if we access the memory 1 byte by 1 byte. And then suppose we have a program stack like this, and then we only have one page of the stack. And then stack now ends in EEBFD000 at this address. And then suppose this buffer is at EEBFD010, which is like 16 bytes above here. Yeah, here. Then our buffer will be somewhere here. We have a 32 bytes, but the 16 bytes belongs to the upper page, but the lower 16 bytes is not mapped at all. Yeah. Something like that. So we could have like this kind of the condition. So one of the buffer can be with the in the middle of like the 2 pages, right? Then when we access this one, buff 0 is here. There is no mapping. So it will generate page fault because we cannot translate this address. Then we need to allocate this memory. Then at the operating system, we can check that, oh, current stack end is this one. And then the faulting address is just right next to the available stack space. Then at the operating system, what we can do is we can check this address from the CR2. And then because that belongs to the right below the normal stack, then operating system can know that, oh, this is happening because the stack overflow happens. Yeah. So we know the reason. Then what you can do is, so read the CR2, and then the reason for fault is like this error from here. Then when we have that, we can allocate a new page, and then now you know that this function, right? With the page insert, we can insert the new stack page to the application, and then do Arabic. Then the user level program will access this again, and now this translation is valid because operating system can successfully back the address. Yeah. Right? So at the first attempt, we could make that stack space empty because program does not use that much of the stack at the start. So it's something like we can do lazy loading of the stack memory, and then we can supply those kind of the memory on demand to reduce like some of the overhead of like if the program does not use a stack for 1 megabyte, and then we don't have to allocate all of them, right? So that we can implement that kind of functionality with this kind of the page fault handling. Any questions about this point? So it's very important to understand like how we can recover the fault. And then I just give the use case that, so we don't know how much of the stack space the program will use. So let's just map just one page. And then whenever the program goes over that limit, then it will generate the page fault because there's no backing page on the stack. And then at the operating system side, if we check the CR2 register, and then that's the near the stack, oh, then that's the stack overflow, back it and continue. That's how we can utilize page fault handler to handle this. And then, so we recovered from the error, and then now user level program can execute without any kind of problem, right? That's why we call this as a fault, because we can recover and continue to execute. And this is a somewhat artificial example of the using of the page fault, because we actually do not use a page fault handler for like automatically growing the step. So after understanding this kind of concepts, I would like to introduce like two other mechanisms that the operating systems, modern operating systems, are actually used with the page fault handling for optimizing some of the resource usage in the operating system. So the first mechanism is called as a copy on write, and then it works as by the name. So what it does is like the copy on write is the technique to reduce the memory footprint. And then what it does is like suppose you are running the Google Chrome web browser, and then Google Chrome web browser, whenever you opens a tab, it will create a new process. And then the binary size, the program size of the Google Chrome is around 80 megabytes or something. Then suppose you are creating a new tab. And that means you need to allocate the 80 something megabyte for the Google Chrome program. New tab, 80 something megabyte for the new tab too. And how many tabs you are opening for the regular day or something. Maybe you guys are discrete guys for the computers, but I'm a crazy guy, so like sometimes I open like the 300 tabs or something. Yeah, that means 300 multiply 80 something megabyte. No, operating system designers are very greedy. So what they are doing is like if we can share the pages. So for example, for the Google Chrome binary, there are some of the read-only sections that will never be changed. In that case, we can share those pages among all the tabs. But the operating system designers do not stop it there. They also shared all the writable pages too, by making them all read-only. So what that means is that, so whenever you fork, so fork means that copying the process environment and then creating a new process from the one. And then when Linux is operating a fork, it does not copy the entire memory space. What it does is like it just copy the page table and page directory and then set it as a read-only. So if there's a one program, there's a fork. Everything gets read-only, and then two process creates. And then in the next execution, either parent or child can make a write access. Then it will generate the page fault because it is read-only, but attempt to write on the memory address. But the interesting thing is that that write should be allowed. The reason is like whenever we do fork, we force all the memory to be read-only, regardless of the real memory permission. The reason is whenever we share the memory because the content was the same. But when the content gets different, then we need to split it. So how we do is whenever you open a new tab or fork, we make an entire thing as a read-only, but regardless of the parent or child, they attempt to do the write access on it, then copy on write. We copy the page for the process that attempted to write, and then apply that memory page to that process only. Then suppose you forked 100 process from the one application. Then all the 100 processes will share the same memory location. We will have just one copy. But while 99 instances are doing nothing, if the one instance attempt to write on the one page, then only for that process, operating system do copy on write. That's how we can utilize the page fault. But no worries, I have some of the diagrams to describe about the copy and write, but I just want to give the high level idea first. And then second thing is about the memory swapping. So the memory swapping is something like your desktop memory is limited by 32 gigabyte or 64 gigabyte, a maximum for the laptop or for now. but you guys have a 1 terabyte of the hard drive. That's not the difficulty in these days. But if we regard the hard drive as a memory, then theoretically, we can run the program that requires a 1 terabyte of memory in your laptop if you have a 1 terabyte hard drive. And the operating system designers would like to enable that in the modern operating systems. And then we also use this kind of a page fault handler. So it's something like at the start, operating systems do not load entire memory. So at extreme, what we can do is just load the 1 page of the program. And then whenever this code attempts to access another page, or it goes to the another page of the execution, then it will generate page fault. And then we as an operating system, we can go to the disk and then get it, map it. Then at the second attempt, it will run. So this is how we could utilize the page fault handler. And let's get into more details about these kind of concepts. So let me describe the copy and write first. So copy and write can reduce the memory footprint, and then this can be implemented with the page fault handler. And then it is a good principle that is applied for all of the operating system for now. Yeah. So think about the operating system 2 server when you are rushing for the deadline for the lab submission due date. Then you guys will use lots of make, GDB, bash, tmux, those kind of applications. But it will run many of maybe the 800 and more processes of those kind of thing. But the operating systems are very greedy. Yeah, it only have 1 copy of the thing, and then it only have the different mappings only if you made the right access to the certain page. Yeah. So this is some of the steps that I did on the last years of some of the right before the due date or something. Yeah. So to just show that we are running lots of same programs in the operating system. Yeah. And to get into a little detail about the program itself. So the programs have the different sections. And then the text section in the ELF is usually refers to the code. And then the reason it is marked as a read-only and then executable, but then not writable, is that in general, there is no reason that the code need to be changed at runtime. So most of the code sections, we regard that as a read-only and executable. And there could be some of the read-only data. For example, you just put some of the string literals on the a code, so as some of the error message or something like that. So that these does not have to be changed. So we put that as a read-only area. But some other data you need to manipulate, then it requires a write access. So some of the access that has a pre-initialized value. Some of the global variable that you initialized with some of the values, they are stored in the data area. And then this .bss, I don't know where this name comes from, but you can regard the BSS as some of the global variables that does not initialize at all. Yeah. And then now I'm talking about the case that we are running same program again and again, right? Then suppose we have 1 copy of the program and then spawn 1 process and the other process, then you can easily think about we don't have to copy the entire memory. So what we can do is, so we just load entire binary like this, and then whenever we create the process, we create the process like this. So that you can think it as these kind of so you can think it as these are the memory mappings. And then the reason why I didn't color that is it does not go to the real physical page for this process. So it will just reuse the existing physical page and then just refer to that. Yeah. But the important thing is that regardless of the original permission, what we are doing is we will mark everything read-only. Yeah. And then do the same thing for the second application. Then the overhead is that we don't do memcopy at all for this kind of thing. Yeah. Then our process creation is much more faster. What we need is just creating page table and directory, No, actually page directory and copy entries, and that's it. Yeah. And then suppose process 1 attempts to write access on this area. Then this is a read-only. So it'll generate a page fault. Then what we can do is we can take a look at the CR2. Then the address is from here. Then another from the error code, we can also see that it attempts to the write access on the read-only memory. Yeah. But although current page table says that it's read-only, we know that which program this process will load at the operating system. And then if we go back to this one and then, oh, this should be read-writable. Then this is a benign fault that should be handled, right? Then we can catch that kind of information by using CR2 and the error code. Then after identifying that, what we can do is like create a writable mapping with the content of that BSS area, and then make it private to that process. That's why it is called as a copy on write. We do not copy anything on the process creation, but whenever there's a write attempt, after analyzing the CR2 and error code, what we can do is copy this BSS, this as RW, and then map it. Then next time we do IRIT, then process 1, it can use this one. But the important thing is that the process 2 can still point here. And then if the process 2 attempts to make an access, then it will not use this one. It will have its own private copy, because there's no guarantee that the change that made by the process 1 will be the same as the process 2, right? So this is the principle of the copy on write. And then you guys can feel about like you guys can reduce amount of memory as at maximum, because we are doing copy if there's a real write that prohibits the memory sharing. Yeah. So the benefits of doing this approach is like we can not only reduce the memory footprint. Whenever we do fork or executing the new program or something, we don't need to load the entire thing on the memory. If it is on the memory, then what we need to do is just create a new page directory table. That's it. Yeah. We don't need to do mem copy. So the program creation or execution speed got also like a faster. Yeah. So there are lots of benefits of doing this. Yeah. So the important thing is like by just making all the things read-only, and then whenever it really needs like the breaking the sharing, then by applying the copy on write with the page fault handler, we can implement that. And the next is about the memory swapping. And I believe that you guys have seen like these kind of a diagram. So for so this is a memory hierarchy. So there's some of the faster memories, such as registers. Registers are also the memory. So it is implemented as a SRAM. So that's why it's fast. So, but it's expensive. So the storage that we can utilize by the registers are very small. But the main memory is several gigabytes, but sometimes that is not enough for doing something. So we might utilize the disk. Then the challenge is that suppose you have only 8 GB of memory, but can you run 16 GB? That's the program that requires a 16 GB. And theoretically, you can do that. So you can do half of the workload and then store it onto the disk and then do half of the work later. So that kind of thing is possible, but can we design the operating system to seamlessly do that? Yeah, then we can actually do that. So even if we have like an 8 GB of memory, so we can theoretically give the application the view of like you can utilize the full memory, the sum of the disk space and then the memory, the DRAM space and etc. And then please work as if you have an unlimited amount of memory. Then as an operating system, we will do everything for you to support that. And then that's actually possible. And then that's already implemented in your systems. And how memory swapping works is the same as like similar to like the page, the copy on write. We just use a page fault handler for that. So suppose you have this kind of the example. So we have a linear virtual memory space. And then for supporting that, we could have a page directory. And then we have two different virtual memory page. And then it could be in a different page table. And then each entry falls into the physical memory. And then suppose we need to remove a page from mapping. And suppose we have a disk here. Then what we will do is we will just remove this page and then store that into the disk. But when we store that, we need to record that this virtual address corresponds to this physical memory. So because the physical memory is the limited one, that we only have 8 GB or something. So we remove one page from the physical memory and store that onto the disk. But later, to look up that, because this kind of the swapped page is unique by the process name and the process ID and the virtual address. So only with the virtual address, we cannot uniquely identify that because of the transparency thing. Yeah. So the application might use like the same virtual address for the many other applications. So to uniquely identify which page it is, so you need to link a process ID and the virtual address, then you can uniquely identify that. So we store that at the disk. And then later, suppose the application accesses this virtual memory address. Then because there's no entry, then it will generate the page fault. Then at the operating system, what we can do is get the CR2 and then get the address. Yeah. And then also get the error code. Yeah. So the error code says that the page is not presenting, but from the address, we can see that if we query the disk, then we can see that if this page is available on the disk or not. So if it is, then when page fault happens, we consult the disk. Then if there is a page, we read that to the disk, and then it does not have to be on the same physical memory address. So it could be on anywhere in the physical memory address. But the important thing is that if we map this using the page table, then get back to the execution. Then later it will work, right? So the summary is that page fault is the popular mechanism that we can handle the fault and do some of the useful things. And then we have learned about like how we can use this for automatically growing the stack, or supporting the copy on write, or supporting the disk swapping. And then from these examples, hope you guys understood like the difference between the fault and exceptions. So page fault, yes, this is a sum of error. But the sum of the error that we intentionally place that, and then whenever that happens, if we can handle that and continue, then we can use that as some of the hooks that the operating system can handle. Yeah. So I believe there are lots of the similarities between the system calls and then page fault to those kind of things, because like it's something like a user space needs something, but we are hiding everything at this layer, and then operating system tries to do something for the application. And then important implication is that if the operating system can handle that entirely seamlessly and transparently, then the application don't know what's happened before, and then they just continue, then it will work. So do you recall that I mentioned about like you guys, so this class is teaching something that is going under the hood. You guys might not seen like that kind of things are happening in your machine. And then the reason why you guys don't know about like those kind of things are happening is that because operating system designers are great. If they did something wrong, you guys have felt about that. So that it's okay that you totally don't know about these things before taking this class, it's all okay, because it's designed to be. Yeah. If there is something bad, then please don't use that operating system. Yeah, that's bad one. Yeah. So and then what I hope is like now you could feel that like what you have learned can be like directly linked with some of the operating system mechanisms here. So swapping, copy and write, those kind of things. So from now on, like the lectures will be much more interesting, because like previously you guys felt like just understanding about the low level mechanisms and not connecting to the high level, but after week 6, yeah, you guys feel more better about like this class, and then we will see much more of like that kind of examples later on. And this is the end of the class for today. And then please feel free to ask any questions about the topic or the labs. And